Hi, hello everybody. I hope that all of you are doing well. So today we will do very nice experiment that can help us to figure out the centripetal force. You know that we studied the centripetal force, and I will try to remind you with some equations what's the centripetal force. But for now, let's show you what do we need for today's experiment. So for today's experiment, we need a balance, and before we use the balance, it is a good idea to try to make sure that the balance is working very well. So I'm using 10 gram here as a standard to make sure that my balance is working, as you can see right here. I don't need to touch it. Yeah, so it is working. That's very nice. What do we need else? We need meter stick, so we will need it, and we will need some washers here, as you can see, and also we will need this system. Okay, so what is this system? Here we have a ball, as you can see, so this ball will be considered as a mass, and then we have a string, as you can see here. This string actually is fixed, it's not rubbery, so it will not be stretched, as you can see. And then this string will be connected to spring, as you can see right here. And then connected to another string, and the other string is connected to this pin right here. And I will show you how to use it, guys. So what I will try to do, I will try, guys, to measure the centripetal force using this system. So when the centripetal force start to work, so the ball will go to the other side, that means there is spring force working on the other side. Okay, so spring force is working on this side, and the centripetal force is working on that side. So the centripetal force is equal to the spring force here. And we will do like two techniques to figure out the centripetal force. So the first technique is the dynamic technique. So we need to rotate this ball, make it move in a circular path, and then we will do dynamic method, which is to measure the weight that can make this spring that you can see right here stretched with the same distance as when we use the dynamic way. So I will show you the dynamic way. So this is method number one that we will use. I will show you that now. So let's do that. Hello everybody. So this is the dynamic way that we will use right now to figure out the centripetal force. So let's do that together. You need to be careful to don't make your hand here moving like this, so then you will lose the center of the circular motion for this ball. So make sure that you keep this pin right here as much as possible fixed at the same point. So this is what you need to do. So rotate the whole system, as you can see right here, like this. So yeah, just to show you how can we do the dynamic method. So this is the dynamic method, guys, and I will show you how to calculate the centripetal force using the dynamic method. So this is method number one. Okay, so this is very nice. Hello everybody. So now what we will do the static method here, and we will try to figure out the weight that stretches the spring to make it with the same length as when we did the dynamic method. So I will show you all of that when we do the calculations, but I will just do my best to show you how to measure this length, guys. So what you need to do here, so maybe I need to have a reference. Yeah, so this can be considered as a reference. So what I need to do now, okay, so I just need to measure the new length of this string that we have right here, okay, and we need to add some masses, and the way that we do add masses actually like this. So we have this connected at the bottom of this ball, and then we add masses one by one, one by one, one by one, until we have the same length as the length of the spring when we did the dynamic method. Okay, so I already used these weights before I record that for you, so I know how much weights do I need to have the same length for the spring as in the dynamic way. So the length was like 0.557 when I did the dynamic way. So now I need to add masses until I have 0.557 meters. And to measure that length, guys, actually we need to measure that. Look at what will happen if I release this system. So you can see that the spring will be stretched, and what I do, I measure this distance. I measure this distance, guys, from the center of this ball to this point right here. And when I do that, of course, I had some help from my son, so he can fix that for me, and I can look at to this measurement. And you can see it's approximately like, approximately it is around like 56 centimeters or 56.5 centimeters approximately. Let's try to show you that. So maybe you need to focus here. So I need to focus here. Yeah, approximately. I know that when I did this, with my son I got better measurements. So you need help to do this kind of measurement. But I did that just to show you what you will get. Okay? So now we have length here. We have length here exactly by adding those masses, of course, exactly as the length when we did the dynamic way, which is to rotate the whole system, if you still remember that. Okay, so now we need to use the weight that we used, and of course the weight actually is this mass plus this mass plus the mass of the ball. Okay, so that will give me the total mass that I need to use to multiply by the gravitational acceleration, so that will give me the spring force, and also will give me the centripetal force. Okay, so I will weight those masses with you right now, so let's do that. Okay, let's weight the masses now. So I have this mass that I mentioned early, and then we have the ball plus this hawk right here, so we need to measure all of that together. So okay, so that gives me like approximately like 415. I will try to calibrate the balance and then measure this weight again. So let's do that, and I will use for this weight, make everything. Okay, make make sure that this will give me 10 grams, so this is very nice. And then weight those masses, as you can see, and then add the ball. So maybe we can have here some space for the ball. Yeah, so for 114.5 grams. So this is the weight that we need to multiply by the gravitational acceleration, so that will give me the centripetal force. Oh, we need to wait. Look at, it's changing, so we need to wait. Okay, so it's 418 now. So always when you weight masses, you need to wait for some time until the balance stable, so then you can have the measurement. So here we have 418, and this is the weight for the whole thing. And as I mentioned, we are measuring this mass for the static method. Okay, so this is very nice. So let's go ahead and do the calculations now. Okay, so guys, here what you can see, so here we did the dynamic method, and if you go to the lab manual, it is actually this method that we have right here. It is actually this method that we have right here, but instead of having this machine, I just rotate this mass by myself, as you can see right here, and I will show you that. So let's try to show you that. So this is what I'm doing, guys. I'm rotating this mass by myself. I don't have photogate, but I'm using this software right here to figure out the periodic time, guys. Okay, as you can see right here. Also, you can see that I have here reference as 1 meter, so I need to have that. And this 1 meter, guys, actually needs to be, maybe I need to move the camera a little bit to this side. So this 1 meter here needs to be at the same plane with this circular motion. If this meter reference a little bit down or a little bit up, so that will give you wrong measurements. So you need to have that exactly on the same plane of the circular motion. And here we have the ball, and also I measured the diameter, so I'm rotating the ball, as you can see here, guys. And of course the spring here is stretched. So I will start, I'm rotating the ball, as you can see, so I have circular motion. I do my best to keep my hand just at the center of the axis, as you can see right here. So that means I have a diameter 0.557 meters. So this is the diameter after I rotate the ball, because the centripetal force will try to stretch the spring. So that's why we have 0.557 meters. But the original, the original length, guys, for the system that I showed you is 51.5. So 51.5 centimeter or 0.515 meters before I do the dynamic method. Before I rotate the system, as you can see here. Okay, so that's very nice. So when we do this rotational motion, guys, maybe I need to move a little bit in this direction. So when I rotate this ball, as you can see, I can track x versus time. And when I track x versus time, I will have this kind of behavior that you see right here. So you can see that we have this behavior, ups and down, ups and down, ups and down. So that means I have, let's count them, I have 1 period, 2 periods, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 periods. This one is not complete, so that's why I have just complete periods. I don't care about y, so x is enough, and that will help me to calculate the periodic time. The periodic time, guys, if I go down maybe a little bit here. Okay, so as you can see, guys, if I click here, so that should give me the time. So we have 0.033. This is the initial time. And if I come to this point right here, so that will give me 7.083. When I subtract, so when I subtract 0.033 second from 7.083 seconds, so that will give me 7.05 second. So the 7.05 second actually is the time for 13 revolutions. I need to divide 7.05 over 13, so that will give me the time for 1 revolution. Okay, so I have the time for 1 revolution from this data that we have right here, which is very nice. And I know that centripetal force, guys, as you can see right here, or you can go to the lab manual, for example. So the centripetal force is equal to mass times centripetal acceleration. So we have mass times v squared over r, and v is equal to 2 pi r, which is the circumference of this circular motion that you see right here, and divide that by periodic time. When we substitute v with what we have right here, so that will give me m times 2 pi squared times r over t squared. I measured the mass of the ball, that's very nice, of the tennis ball. So I got 57 times 10 to the power minus 3 kilogram, as you can see right here. So that's very nice. And I measured r, which is 0.557 meters, and I got that from here, guys. So I measured this distance that you can see right here. So you can see here that we have 0.557 meters. So yeah, so that's very, so we know all of that, which is great. So now what we can do, we can substitute t with the periodic time, substitute r with 0.557 meters, and then do the calculations. And when we do the calculations, guys, so what will happen, you will see that centripetal force is equal to 57 times 10 to the power minus 3 kilogram. Here we have 2 pi squared, I have 0.557 meters, and we have here t squared. So when we do the calculations, so that will give me here 4.2624 Newton. That is very nice. L0 and L here, I just try to show you that. I just try to show you that this is the length of the system, guys, that I showed you before we do the rotational process, before we rotate the whole system. Okay, and 0.557 meter, so this is the radius that we have from here. So that's why I have L and I have L0. So L and L0. Okay. So let's now come to the mass that we measured. What we calculated here, we calculated the centripetal force using the dynamic method. Okay? Using the periodic time and the radius of the circular motion and all of that. Okay, so as you can see here, guys, so now we try to measure the gravitational force from the static method. You still remember when we added the masses to stretch the spring. So the masses that we added to stretch the spring actually is 0.41 kilogram. Okay, when we multiply that by the gravitational acceleration, as you can see right here, so that will give me the gravitational force or the spring force, which is actually is equal to the centripetal force. So you can see that we have 4.096 newtons. So use the lab manual if you would like. So the lab manual also is clear, and I would like you guys, yeah, so there's no big difference, guys, just we use like different setup than what we have in the lab manual. So just answer those questions. And actually, guys, to calculate the uncertainty, so I taught you how to do that. So you know how to calculate the uncertainty, guys. So these are the equations that you need to use to calculate the uncertainty. So the smallest value that my balance measure is 0.1 gram. So you can use that. You can use the idea of a single measurement uncertainty. So that's possible. And also the meter stick that I have can measure as smallest value, of course. It can measure 1 millimeter. So this is the smallest value that my meter stick can measure. Okay, and you can again use the idea of single measurement uncertainty, and you can calculate that. So that's not complicated, guys. Just answer these questions and you will be okay, guys. And again, instead of using what we have right here, I just used this idea, so that can help you to figure out the centripetal force, as you can see. So yeah, that's very nice. So yeah, thank you so much, guys, and see you next time. Yeah, okay.